Okay, so imagine you're an engineer, maybe a computational physicist, right? And you got this really, really tough modeling job. Think like a complex underground reservoir with lots of layers, or maybe some composite material with fiddly internal bits. You hit this wall almost immediately. The more realistic detail you need, the bigger the computational cost. It just explodes.
Absolutely. That's a classic headache in computational solid mechanics, when you have complex geometry or materials that change properties all over the place. Capturing those tiny important features means the standard ways of doing things, these single-scale methods, they just don't scale well. Your computer grinds to a halt.
So today, we're going to really dig into a fascinating way around that problem. It's a computational technique the researchers behind it call. Okay, get ready for this. Stress mixed polyhedral finite elements for two-scale elasticity models with relaxed symmetry.
Laugh slightly. It is a
Okay.
mouthful, isn't it? Thankfully, they shortened it to MFM-WS, much easier.
Much easier. And our mission today is to unpack what that actually means for you. We want to show how this advanced approach gives you really accurate, detailed solutions.
And crucially, it does it more robustly and faster than the old methods, especially for these 3D elasticity problems. Think of it like getting surgeon-level precision, but without needing the insane computational power you'd expect. It's a clever shortcut.
Okay, let's build this up. The basic problem we're solving is linear elasticity. And that means we're usually tracking two key things, right? Stress, which we call sigma, and displacement.
That's right. And often we set up the math using what's called the Hellinger-Reisner formulation, but that immediately throws up a couple of big roadblocks.
Roadblocks, like the cost we just mentioned.
Yes, cost is one. But there's another more subtle mathematical issue that pops up, something called locking phenomena.
Ah, locking. Yeah, I've heard of that. That's when you're trying to model materials that are almost incompressible, isn't it? Like rubber or materials where the Poisson ratio gets close to 0.5.
Exactly. Standard methods, particularly these stress-mixed methods, they just sort of seize up. They lose accuracy dramatically when you get near that limit. It's a real barrier.
And wasn't there another difficulty tied into that? Something about making the stress tensor symmetric.
Yes, precisely. Mathematically, the stress tensor should be symmetric, but building finite elements that strictly enforce that symmetry while also being stable, especially near that incompressible limit, it's really, really hard.
So the researchers were facing two big challenges, making the element construction easier and stopping this locking problem. How did they uh, manage that stability fix?
They did something quite clever. They introduced a third variable into the mix, rotation, which they called dollars.
Wait, hold on. We want things simpler, but they added another variable. How does that help?
It seems backwards, I know. But this rotation variable, dollar, acts as what's called a Lagrange multiplier. Its whole job is to weakly enforce that symmetry constraint.
Okay, weakly enforce. So instead of forcing sigma to be perfectly symmetric right from the start, which causes all the instability problems. Yeah.
They use this Tavre variable to make sure that the difference between sigma and its transpose, sigma sigma te, averages out to zero in the solution space. It satisfies the constraint, but in a more relaxed way.
And that relaxation is the key. That's the relaxed symmetry part of the name.
That's the core idea. By relaxing that strict symmetry requirement, they found it much easier to satisfy another crucial condition, the divergence compatibility condition, and that's absolutely essential for the method to be stable and mathematically sound. Introducing dollars gives you that needed flexibility.
Okay, that makes sense mathematically. But how do we know it actually works in practice? Did they prove it avoids locking?
They did. The numerical analysis in the paper is rigorous. They derived error estimates for this MFMWS method, and crucially, those estimates are completely independent of the Poisson ratio.
Independent. So it doesn't matter if you're close to 0.5 or not.
Exactly. That's the gold standard proof. It confirms the method doesn't suffer from locking near the incompressible limit. So, stability. Check.
Brilliant. Now let's talk efficiency, because stability is great, but we started this by talking about crippling computational costs. This is where the two-scale part comes in, right? Gameth Genge.
Yes. The two-scale architecture is where the magic happens for efficiency. You can think of the whole problem domain, like our complex reservoir, as being broken down into smaller, manageable chunks, like polyhedral blocks or elements.
Okay, breaking it down.
And the method uses two different refinement levels. There's a coarse scale linked to a parameter gammas, and a fine scale linked to gamma scale.
What do those scales control?
The coarse scale, gamma, deals with the skeleton of this breakdown.
The scale, you mean like the edges and faces where these polyhedral blocks meet?
Exactly. It's the network of boundaries between the subdomains. This coarse parameter, gamma, controls how accurately we calculate the traction that's the normal force component across these boundaries.
Okay, so coarse scale handles the interfaces. What about the fine scale, gamma?
That governs how refined the calculations are inside each individual polyhedral block inside a megaehlers. So you have a coarse view of the connections and a potentially much finer view of what's happening locally within each piece.
Right. So we've chopped up the problem. But just chopping isn't enough for speed, is it? You mentioned a secret weapon, static condensation.
Ah, yes, static condensation. That's really the engine driving the efficiency. It's a way to split the problem into a global part and many local parts.
Global and local. How does that split work? What variables go where?
We divide all the unknowns into primary variables and secondary variables. The primary ones are solved together in a single, relatively small global system. The secondary ones are handled locally inside each polyhedron.
And what are these primary variables that get solved globally? What takes up the main computational effort?
The global system is dramatically smaller because it only includes the coarse scale primary variables. These are essentially two things. That traction variable we talked about living on the skeleton.
The Lagrange multiplier connecting things.
Exactly. And the other part is the rigid body motion components of the displacement within each polyhedron, basically, how each block as a whole might translate or rotate.
Okay, this is the really clever part, isn't it? If you're only solving globally for stuff happening on the boundaries and the overall block movements, aren't you just shifting the computational work from the inside to the surfaces?
You are shifting it, but you're shifting it onto a much smaller set of unknowns. The skeleton, the network of faces, has far fewer degrees of freedom than the entire volume. You concentrate the main global computational effort there.
And the fine details. The stress and displacement inside the blocks.
That's the beauty. Once you've solved the small global system for the tractions on the boundaries, that traction information becomes the boundary condition for independent problems inside each polyhedron.
Independent, so each block can be solved on its own.
Completely independently. These are local Newman problems. You solve for the secondary variables, the detailed internal stress, displacement, and that rotation variable $2 within each block, using the globally computed traction as input.
And because they're independent, you can solve them all at the same time, in parallel.
Precisely. That's the massive win for efficiency. You can throw as much parallel computing power as you have at these local problems. The size of the expensive global system doesn't grow. It stays relatively small.
Wow. So you solve a small global problem, then unleash parallel computations for the details.
Yeah.
And this isn't just some clever hack, it's mathematically solid.
Absolutely. The paper actually shows that this whole MFMWS formulation is mathematically equivalent to another established approach called a multiscale hybrid mixed, or MHMWS method. That equivalence basically proves it's built on a sound theoretical foundation.
Okay, so we've got robustness, no locking. We've got efficiency thanks to static condensation and parallel local solves. What about the third pillar, accuracy? Does simplifying the global problem mean we lose precision?
You might think so, but actually, no. In fact, the theory predicts the potential for enhanced accuracy rates compared to standard methods, especially for certain outputs.
Enhanced accuracy. How does that work? How can being coarser globally lead to better results?
Well, it's nuanced. The errors in the main stress and rotation fields are primarily driven by that coarse skeleton discretization, gamma. So you'd expect maybe log +1 convergence, which is standard.
Okay, that sounds normal.
But here's the kicker. Because you have all that freedom inside each polyhedron with the fine scale gamma, you can get much better accuracy for the divergence of the stress, nabla sigma.
Wait, the divergence gets better just by refining inside the blocks, even if the global mesh stays coarse.
Yes. You can crank up the polynomial degree used for the internal calculations. This is computationally cheap because it's local and parallel. And the theory shows this can push the convergence rate for the divergence way up, potentially to 1 plus t plus 1. You get arbitrarily high accuracy there.
That feels like, like getting extra performance for free almost.
It's not quite free, you pay with local computations, but it's cheap. And it doesn't stop there. The displacement accuracy can also get a boost. It can reach an enhanced rate like ol plus 2, which is 1 order higher than the typical +1 you might get otherwise.
So by spending cheap, parallel computing effort on the local details, you actually improve the accuracy of the overall global solution significantly.
That's the idea. The decoupling lets local refinement really punch above its weight in terms of global accuracy. And there's another practical advantage we should mention: geometric flexibility.
Oh, right. The method uses general polyhedral meshes, not just nice, neat cubes or tetrahedra.
Exactly. These are sometimes called polytopic methods, and that flexibility is hugely valuable in the real world.
Why is that so important?
Because real engineering problems rarely involve perfectly simple shapes. Think about modeling flow in underground rock formations. You've got complex layers, faults, fractures, or composite materials with weird internal structures. Polyhedra let you create meshes that conform much better to these complex geometries.
So you can tailor the mesh to the problem's features.
Yes. The researchers even showed this works well on highly irregular meshes, specifically Voronoi meshes. They demonstrated that the method still achieves its predicted convergence rates, even on these, let's say, geometrically challenging grids.
Okay, theory sounds great, flexibility is great, but the real proof is in the pudding, right? The numerical tests. They ran simulations to back this all up. What did test case 1 show? It was twisting and compressing a cube.
That's right, a standard benchmark problem. They used a specific variant of the method, an enriched one, and systematically tested the effect of increasing that internal polynomial degree while keeping the main skeleton mesh fixed.
And did it confirm the theory about improved accuracy?
It did. Just as predicted, increasing systematically improved the accuracy for the divergence of stress and for the displacement, confirming those enhanced convergence rates we talked about.
Okay, good confirmation. But wasn't there something even more striking about efficiency that came out of a different test? The space-based convergence study.
Ah, yes. That was really interesting. Instead of the standard approach where you just make the entire mesh finer and finer to get more accuracy.
Which makes the global problem bigger and bigger.
Exactly. Instead, they kept the overall coarse structure, the macro partition, fixed. They only refined the mesh on the skeleton and the mesh inside the elements in place. The question was, how much accuracy can we squeeze out of this fixed coarse layout just by tweaking the scales?
And the result? How much did it save computationally?
It was dramatic. They reached the target accuracy level, but the number of degrees of freedom, the size of that condensed global system they had to solve, was reduced by more than 1 order of magnitude.
Wow. 10 times smaller.
Yeah.
Compared to just making the whole mesh finer.
At least. Imagine solving a global problem that's 10 times smaller to get the same precision. That's a massive saving in computational time and memory, especially for really big problems.
That really drives home the efficiency point. And wasn't there something else they observed in that study? Something about superconvergence.
Yes. Critically, they observed superconvergence. This means the accuracy improved even faster than the standard theoretical rates predict specifically, by about an extra half order in the convergence rates.
How does that happen? Where does the extra accuracy come from?
It seems to arise from the way the local problems handle the solution details. By solving things independently within each element, you can smooth out or resolve error components more effectively than a purely global method might. You're leveraging that cheap local computation again, and it pays off with unexpectedly fast global accuracy improvements.
So, invest locally, profit globally with extra accuracy. That's the essence of this computational
I
shortcut.
got it. And they didn't just test on simple cubes. Test case 2 really pushed the method's robustness.
Right. This was the challenging one, the highly heterogeneous material.
Yeah, a complex elastic domain designed to mimic geological layers. It had 16 different layers, each with varying material properties. It was based on a standard benchmark suite, the HPC-4E test suite, really designed to stress test numerical methods.
And how did MFMWS perform?
It performed beautifully. They compared the multiscale solution against a very fine single-level reference solution. As they refined the skeleton mesh of the multiscale method, its solution converged perfectly to the reference solution. It proved the method remains stable and accurate even when dealing with these complex, rapidly changing material properties that can often trip up other methods.
Okay, let's wrap this up then. We started with the big challenge. Modeling complex solids is computationally expensive, and standard methods can fail, especially near incompressibility due to locking.
And we've seen how this MFMWS method tackles that head-on. It's robust, it avoids locking, it's flexible, it handles complex polyhedral geometries, and crucially, it's efficient.
Super efficient, thanks to that static condensation, the global-local split, and the fact that those local solves are massively parallelizable.
Right. The core achievement, I think, is delivering highly detailed, fine-scale information, the stress, the displacement, the rotation accurately.
Well, only needing to solve a much smaller, manageable global problem that just focuses on the coarse scale information at the boundaries between elements.
It really is a shift in thinking about how we break down and solve these large-scale physics problems.
So we'll leave you, our listener, with a final thought to chew on. If these kinds of sophisticated mathematical tools let us get higher accuracy, even superconvergence, by cleverly focusing our computational effort just on the interfaces within a complex structure, what other basic assumptions do we hold about how much brute force computation is really necessary? What other complex physics or material behaviors might be vulnerable to this kind of smart, multi-scale, localized approach next?